Hello students. Now today's topic is the atomic spectra. Let's begin with this topic. Hydrogen spectrum and spectral series. So students, we know that in an atom, electrons have discrete and specific energies. These are, or there are more energies state in the atom than there are in electrons. When an electron transition from one energy state to another energy state, it will be emit some light, which we are saying that photon, with a specific wavelength. So, in a given set of this condition, we have a collections of a wavelength. In what we are constituting, this will be an atomic spectrum. So, when an hydrogen atom is excited, it returns to the ground state by emitting the energy it has absorbed earlier. This energy is given out by atom in the form of radiation of different wavelength, and electron jump down from higher to the lower orbital state. Transition from different orbit states causing different wavelength, as I told you earlier students. As you can see this, when electrons jump from ground state to the excited state, this will be happen only when electrons get some sufficient types of energy. After 10 to the power minus 8 seconds, it will lose their energy in the form of a photon and come back again in its initial stage. If a photon goes the state of lower energy state, it emit photon. Okay. These constitution spectral series, which are characteristics of the photon emitting them. When observed through a spectroscope, these are imaged as sharp as straight vertical lines of a straight color. Spectral series of hydrogen spectrum. The spectral lines arising from the transition of electron from spectral series. Mainly there are 5 spectral series, and each series named after the discovery of a Lyman series, Balmer series, Paschen series, Brackett series, and Fund series. Some are calling this is a P fund, okay, of Fund series. But here we are pronouncing as a Fund series, okay. So these are basically 5 series. According to the Bohr's theory of a wavelength of radiation emitted from hydrogen atom is given by 1 by lambda is equals to R 1 by n1 square minus 1 by n2 square. What is the mean of R? Students, here the mean of R is Rydberg constant. This is a Rydberg constant whose value is 1.097 10 to the power 7. So from here we can calculate the value of lambda also, by which the actually photon is radiated. That means the color of photon which we can generalize, that can calculate it from here. N2 is the outer and N1 is the inner orbit. As we can see in the spectral series, they have a different kind of lines like absorption spectra, emission spectra, ionization spectra, or more. So from this image, it is equivalent that atomic hydrogen emission spectrum is divided into the number of lines, as you can see. Okay, so these number of lines divide into the spectral lines of a wavelength, different kind of a wavelength, and that wavelength we can like derived or which can get given by this Rydberg formula. The observed spectral lines in the hydrogen emission spectrum, as we can see, This will be due to the atomic transition between the different energy states or different energy levels. The spectral series are important in astronomical spectroscopy. So to know about the emission and absorption spectral in detail, so let's begin the detail wise study. Like using the Rydberg formula, as I told you, what is the Rydberg formula? So earlier, which formula we saw that 1 by lambda is equals to rz square, 1 by n square minus 1 by n square. Or we can say 1 by n1 square minus n2 square, where r is the Rydberg constant. As I told you, this is in meter. So this is in meter inverse. The value of r, as I told you, 1.097 10 to the power 7 meter inverse. Z is the atomic number. N is the upper energy level, as I told you. If I'm just writing in a n prime, so this is a n prime and simply n. Okay, so n prime is the n is the upper energy level, whereas n prime is the lower energy level. Lambda is the wavelength of light. Lambda is the wavelength of light. So, and if Z is what? So, in a spectral series, single electron atom like a hydrogen, Z is equals to 1. So, for Lyman series, if I'm just calculating the value for a Lyman series, the value of n lambda. So, n prime is equals to 1. So if n is equals to 2, the value of lambda, which is emitted 121.57 in nanometer. If 3, so the value of a lambda is 102.57. Similarly, if infinite, I'm just saying, so this value comes 91.75175, and similarly, this further value we can calculate. So few values I just mentioned, like these value for the this is the for the Lyman series. For the Fund series, as I told you, and if n prime is equals to 5, so the value of n, the value of lambda, if the value of n is 6, so this will become 745 or 60 in nanometer. If the value of n is 7, so this comes 4654 nanometer. If this value is infinite, so this comes 2279 nanometer. And similarly for the Humphreys series, there will be number of a series will be there. So for the Humphreys, Balmer series, Paschen, bracket, like if I'm just taking Balmer. So for Balmer series, n prime is equals to 2, as we can see here. N prime is equals to 2. So for that, like final should be more 3, 4, infinite, like that. So if this will be 3, the value of lambda comes 656.3. If 4, so 486.1. If infinite, so 364.6. Similarly, as a Paschen series, if the value of a 4, for Paschen series, as we can see, like n will be start from 3. So if n prime is equals to 3, n will be 4. If so, 1875. If this will be infinite, so 820.4. This value we receive. As like a bracket, we can calculate also. For bracket, which is not mentioned here, like n prime is equals to 4. So for that, like 5, 6, and for the case of infinite, if the case for 5, like initially they have like a particle is moving from 5 to 4. So the radiated wavelength will be 4051. If this will become 624, so 2625, and for the case of infinite 1458. So these are the values some which we will get. This is the value of a wavelength actually which we will receive by this by applying the formula of a Rydberg formula. Because of that, we can easily study about the atomic spectroscopy where we get the absorption line and for the like emission line also. So this is the absorption line, this is the emission line. When the particle moves from higher energy to lower energy to the higher energy, it will be absorb some energy, and when the higher to lower, it will be some like emit some energy, which we can say in the form of emission will be in the form of photon. And if the energy will be from higher to the upper higher, so this will be ionized energy. These are the spectral lines. As you can see. So for Lyman series, these are the wavelength. For the case of infinite, as I told you, for the case of initial value. Lyman series. Lines corresponding to the transition from outer energy level n is equals to 2, n2 is equals to 2, 3, 4 up to infinite to the first orbit is called n1. Constitute the Lyman series. The wave number of a different line are given as nu bar is equals to 1 by lambda is equals to r times 1 by 1 square minus 1 by n2 square. n2 could be 2, 3, 4 up to infinite. Lyman series lies in the region of ultraviolet region of electromagnetic spectrum. Balmer series. Lines corresponding to the n2 is equals to 3, 4, 5 up to infinite to n1 is equals to 2 constitute Balmer series. The wave number of different lines are given by nu bar is equals to 1 by lambda is equals to r 1 by 2 square minus 1 by n2 square. So Balmer series lies in the visible region of electromagnetic spectrum. The series is obtained only in the emission spectrum. Same in the case of Paschen series. Lines corresponding to the n2, 4, 5, 6 up to infinite to n1 is equals to 3 constitute Paschen series. The wave number of different lines are given by nu bar. What is the nu bar here, students? Nu bar is a wave number is equals to r times 1 by 3 square minus 1 by n2 square. Paschen series lies in the infrared region of electromagnetic spectrum. This series is obtained only in the emission spectrum. Similarly, as we have a bracket series, this series corresponds to the transition n2 is equals to 5, 6, 7 up to as an infinite, whereas n1 is the 4. The wave number of the different line is given by nu bar is equals to r times 1 by 4 square minus 1 by n2 square. Bracket series lies in the infrared region of electromagnetic spectrum. Similarly, we have a Funde series. This series corresponds to transition from n2 is equals to 6, 7, 8 up to infinite. Students, we must have to take n1 is equals to 5 because this is the fifth series. The wave number is given by nu bar is equals to r times 1 by 5 square minus 1 by n2 square. Funde series lies in the infrared region of electromagnetic spectrum. So now we are moving with some master's MCQ questions. The first question is for you is lines corresponding to transition from outer energy level n2 is equals to 2, 3, 4 up to infinite to the first orbit n1 is equals to 1. Constitute first Balmer series. Lyman series, Fund series, Paschen series. Just tell me, students. The correct answer is Lyman series. Paschen and bracket series lies in the region of electromagnetic spectrum. Option ultraviolet. Next, infrared, visible. None of these. The correct answer is infrared. Balmer series lies in the region dash of the electromagnetic spectrum. Ultraviolet, infrared, visible. None of these. The correct answer for this question is visible region. I hope you understand the complete series of a atomic spectrum. If there is any doubt, you can ask in the chat session, in the comment section, student. Till that, take care everyone.